working as a disruptor to pick up middleware design. My name is Lan Vong. I'm from IBM, technical evangelist for extreme transaction processing, focusing on web to extreme scale. Today we'll discuss how traditional environments are designed and how middleware was designed to fit those environments. Next, we'll discuss the cloud-based environments and how this has an impact on middleware, how it has to evolve to remain cost competitive. First, let's take a look at traditional environments. Typically, projects are funded to purchase machines dedicated for a given purpose. These machines are dedicated to a particular project and for their needs only. These boxes are assigned a permanent network address, host names, and installed to a given data center. These boxes are thought of as permanent, and they stay around until they break or are upgraded. Since these machines are assumed to be around for a while, their host names don't change, and a lot of middleware is designed to reference these host names directly. Let's take a look at how traditional middleware is designed based on these assumptions. Middleware was designed to know information about each box, host name, and IP address. Each box can store state like message stores, transaction logs, diagnostic logs, and so on. As a result of this design and all of these assumptions, customers focus mainly on topology rather than deploying an application. You can see this in the case of WebSphere application server. You would normally set up a cell, federate nodes into that cell, define a cluster, add members, and then finally deploy the application to the cluster itself. Each of these machines are different. Each of them have been tuned and configured accordingly so that they work in this environment. With the various information, there's not a lot of patterns or templates in this design. Customers had to know how to integrate each of these pieces together, the various components that make up this environment. This is a very manual, labor-intensive step. It's not automatic or cheap. Given that the boxes were typically permanent, many middleware products do not include high availability out of the box. You could buy third-party products like SunCluster, IBM ACMP, or Veritas Cluster Manager, but these products are typically very expensive and take time to configure. Once they were configured, though, they would remain that way and up and running for potentially years at a time. Since these products were only needed to be configured at one point in time, they were not optimized. Rare events are not optimized for. You only optimize things that you have to do on a daily basis, that you have to do over and over again. Since once you set up high availability and these boxes were permanent, stayed around for a long period of time, they were not very easy to configure. A lot of the products did not include high availability features that were easy out of the box. If you did want to remove this box because of an upgrade or a failure, you had to remove some topology from any middleware using it. You had to run, in the case of WebSphere, a remove node, make sure there's no other machine in the environment referencing it. Make sure that any state remaining on that box isn't useful anymore and that you're not losing data. Potentially, you would also need to configure another box to back up that data. Any existing state, any logs that were remaining on that box might have to be migrated to a different box for recovery reasons. You would also need to reconfigure any of the high availability, labor-intensive steps that you had done before, any of the high availability quote stuff that you had to do perhaps years ago. You had to unconfigure it, basically. You can't just turn off the box and forget about it. There's a lot of manual steps again, to remove a box from the environment. Most middleware stacks are not designed to run active-active in a multiple data center. Data centers are expensive. We have a few large customers that do have more than one, but typically, even in this case, when they do have multiple data centers, say 2 or 3, they run in an active-passive mode. They don't have applications running, being routed to both data centers at the same time. Typical design is there's only one database, even in the multi-data center environment, and this database is only in one data center, with the application deployed in that same data center. The second data center is typically cold, and it might be used as a test system, but it's not accessed, as frequently as a first data center. And most centers don't charge for the software that's running in the standby data center, so they don't, optimize for it. The software is not designed to have both of these data centers running active. Again, a lot of the middleware software is not designed to take account. They're not designed for this active-active mode, so there's no concern for network latency. If you happen to have a request going into the second data center and your database is still in the first data center, there's a potential for slow response times to have to go across the network and get that information and return it back to the user. This usually performs very badly and could cause issues in your environment depending on if you have, SLAs configured or not. So when, customers buy these boxes that are dedicated for a particular project, they have all the memory that they require for a given application. This way, applications can they have free reign. They can be designed to use a lot of memory. Typically, they would have caches within the local JVM itself to cache data. But there was really no regard for, I wouldn't say no regard, but, since they had access to specific machines that they had handpicked with all the available memory that application needed, there was really no need to kind of redesign the application, make sure it wasn't using that much memory. And people started to look to 64-bit to handle these bigger caches as, the application and the environment scaled up. But we'll see that perhaps this is not the best solution as virtualization takes over. So typically in the past, this is you would store all of your state in a database, and when you have a camera, everything starts to look like a nail. So any application data, any application state was stored in the database. Again, this could cause huge problems if you had multiple data centers and you were routing a request to the data center that did not contain the database. It would have to go across the WAN and get its data. But what people didn't realize is that depending on the type of data that you're storing and how long it needs to be around for, how long it needs to have access to it and high availability to that data, you can have different options for storing that piece of information. Data grids offer an elastic state solution for storing data that needs to be fault tolerant and shared between applications, but doesn't need to be around for months, years, and so on. This data grid option is a very good solution for application data like HTTP session state that only needs to be around for as long as the session is alive, say 30 minutes or an hour, depending on the application itself. Not all of the state needs to be